Every single galaxy is part of one vast, invisible structure. This cosmic web is the universe's largest architecture, a network of dark matter and gas connecting everything in space. By the end of this, you will understand the hidden blueprint that dictates the life and death of galaxies. We will uncover how this web was first discovered and explore the mind-bending theories that explain its very existence. What does our own galaxy's specific location within this cosmic network reveal about our past and our future? Mapping the heavens required a new kind of astronomy, one that catalogued the locations of galaxies on an unimaginable scale. For centuries, our view of the cosmos was like looking at a few scattered trees, missing the forest entirely. Then came the great surveys. Projects like the Sloan Digital Sky Survey pointed telescopes at the sky night after night, not to take pretty pictures, but to collect precise data on the positions and distances of millions of galaxies. They did this by measuring redshift, the stretching of light from galaxies moving away from us, which tells us how far away they are. When they plotted all these points in 3 dimensions, a breathtaking pattern emerged from the noise. It was not a random scattering of stars and systems. Instead, galaxies clustered into colossal walls, millions of light years across. They stretched out in long, delicate filaments, like threads in a spider's web. And between these structures lay the voids, immense deserts of near-empty space, so vast they are almost incomprehensible. This was the first direct glimpse of the cosmic web. Theorists had already predicted such a structure, born from the gravitational influence of invisible dark matter. But here was the proof, a cosmic blueprint drawn from observational data. This discovery was a turning point, proving the universe is organized, interconnected, and structured on the grandest of scales. Seeing this hidden architecture for the first time forces a simple, profound question. What exactly is holding this entire web together? The answer lies in a hidden architecture of truly cosmic proportions. This is the framework of the cosmic web, a vast and intricate network built from dark matter. Think of dark matter as the invisible threads of a spiderweb, threads we cannot see directly but whose strength holds everything together. This dark matter scaffold is the most fundamental structure in the universe. It forms long, delicate filaments that can stretch for hundreds of millions of light years across the emptiness of space. These filaments are the great cosmic highways, connecting the most crowded places in the universe. Where these filaments intersect, they create dense knots known as nodes. These nodes are the metropolis areas of the cosmos, home to immense clusters containing thousands of galaxies, all bound together by gravity. But between these brilliant threads and shining nodes lies something else entirely: the cosmic voids. These are the empty deserts of space, regions of breathtaking emptiness that can span hundreds of millions of light years. They are not completely empty, but they are so sparsely populated with galaxies that they appear as vast, dark bubbles within the web. This entire structure, with its dense nodes, connecting filaments, and empty voids, creates a cosmic hierarchy. It is a universal infrastructure that dictates where galaxies can form and how they will evolve. The flow of gas, the collisions of galaxies, the very birth of stars, all of it is guided by this underlying framework. This invisible architecture does not just house the galaxies, it actively shapes their destinies. So, what is this invisible substance that dictates the shape of our universe? It is dark matter, the primary architect of the cosmic web. Dark matter is fundamentally unlike anything we are made of. It does not emit, absorb, or reflect light. It is completely invisible to every telescope we have ever built, yet its gravitational pull is the single most powerful force sculpting the cosmos. In the very early universe, the distribution of matter was almost but not perfectly smooth. Tiny, random fluctuations in the density of dark matter existed like faint ripples on a pond. Over billions of years, gravity relentlessly amplified these ripples. Regions with slightly more dark matter pulled in more matter, growing denser and denser, while emptier regions were left behind. This process caused the dark matter to collapse into the vast, interconnected network of filaments and nodes we observe today. The evidence for this invisible builder is overwhelming. In the 1970s, astronomer Vera Rubin studied how stars orbit the centers of spiral galaxies. She found a profound mystery. The stars at the outer edges of galaxies were moving just as fast as those near the center. According to the laws of gravity and the amount of visible matter, these outer stars should have been flung off into space. The only explanation was that each galaxy was embedded within a massive, invisible sphere of dark matter, its gravity holding the entire galaxy together. Her work proved that what you see in a spiral galaxy is not what you get. There is far more to the universe than meets the eye. We can also map this hidden matter directly through a phenomenon called gravitational lensing. The immense gravity of a dark matter filament warps the fabric of space itself, bending the light from distant galaxies that passes near it. This acts like a cosmic magnifying glass, distorting the shapes of those background galaxies. By carefully measuring these subtle distortions, astronomers can trace the outline of the invisible dark matter, revealing the hidden scaffold of the cosmic web in stunning detail. This elusive substance, which we cannot see or touch, is the master builder. Its gravitational dominance is the unseen hand that assembled the grand architecture of the universe, proving that the cosmos is ruled not by what shines, but by what hides in plain sight. The blueprint for this entire cosmic structure was stamped into the universe at its very beginning. In the first fleeting moments after the Big Bang, a period of incredibly rapid expansion called cosmic inflation occurred. During this explosive growth, the empty vacuum of space itself was not perfectly smooth. It was fizzing with tiny, random quantum fluctuations. As the universe inflated at a staggering rate, these subatomic ripples were stretched to enormous, macroscopic proportions. They became the faint hills and valleys in the density of matter and energy, the primordial seeds from which everything would grow. We can actually see a fossilized image of these seeds. It is the cosmic microwave background radiation, the ancient afterglow of the Big Bang that fills all of space. This radiation is a snapshot of the universe when it was just 380,000 years old, a time when it cooled enough for light to finally travel freely. Space missions like the Planck satellite have mapped this faint glow in exquisite detail. The map reveals a mottled pattern of slightly warmer and cooler spots. Each of those spots corresponds directly to those initial density fluctuations imprinted by inflation. The warmer regions are the hills, the areas with slightly more matter. The cooler regions are the valleys, the areas with slightly less. This map is the universe's baby picture, and it contains the complete genetic code for the cosmic web. Every filament, every cluster, every vast void we see today was already encoded in that primordial fingerprint. From these humble beginnings, the force of gravity took over. Over billions of years, it pulled on those dense hills, drawing in more and more dark matter and gas. The valleys were left to empty out, becoming the cosmic voids. The entire sprawling tapestry of the modern universe, with its brilliant galaxies and dark connecting threads, was woven from these infinitesimal threads. With the universe's blueprint imprinted upon it, the cosmos needed a force to do the construction. That force was gravity. It is the master sculptor. the relentless artist that took those faint primordial ripples and carved them into the grand architecture we see today. Gravity's work was a slow and patient process spanning billions of years. It began by focusing on the slightest overdensities, those hills in the cosmic landscape where dark matter was just a tiny bit more concentrated. The gravitational pull of these regions started to attract more and more dark matter and gas from the surrounding space. Think of it like water slowly draining towards the lowest points in a landscape, only in reverse. Gravity pulled matter towards the highest density points. As more matter was pulled in, the gravitational pull of that region grew even stronger, accelerating the entire process in a powerful feedback loop. This is gravitational collapse, the engine that built the universe. But this was not a simple, uniform process. Structure formed in a hierarchy. Small clumps of dark matter formed first, and then these clumps, drawn together by their mutual gravity, would merge to form larger and larger structures. It was a cosmic dance of accumulation, where tiny villages of matter merged into towns, then cities, and finally the immense metropolitan clusters we find at the intersections of the web. This gravitational dance was not merely a straightforward pull. It was a complex interplay of motions that created the web's specific morphology. As matter flowed along the emerging dark matter filaments towards the dense nodes, it left behind the vast, emptied-out regions we call the cosmic voids. The entire process is a breathtaking demonstration of how a single, simple force can generate staggering complexity. We can witness this entire cosmic evolution unfold inside a computer. Simulations like the famous Millennium Simulation start with a universe that is almost perfectly smooth, seeded only with those tiny initial fluctuations. They then program in the known laws of physics with gravity as the dominant force. When they press play and let the simulation run for billions of virtual years, something remarkable happens. That smooth, featureless early universe consistently evolves into an intricate filamentary network, a perfect digital replica of the observed cosmic web. It is a powerful confirmation that gravity alone is the architect. This sculpting is not a relic of the distant past. Gravity's persistent pull ensures the cosmic web continues to evolve even today, with filaments tightening and galaxies streaming along these invisible highways in an endless, slow-motion ballet. But if this cosmic architecture is built from invisible dark matter, how can we possibly see it? We are in the position of someone trying to map a city at night by watching the movement of its people. We cannot see the streets or the buildings directly, but we can see where people gather and how they flow from one place to another. Astronomers use a similar principle, employing brilliant indirect methods to trace the outline of the unseen. One of the most powerful tools is gravitational lensing. The immense mass of a dark matter filament warps the very fabric of space around it, creating a sort of cosmic lens. When light from a distant background galaxy travels through this warped space, its path is bent. From our viewpoint, that galaxy's image appears stretched and distorted into faint, ghostly arcs. These subtle distortions are the telltale fingerprints of the invisible mass. By meticulously measuring the warped shapes of millions of distant galaxies, we can literally map the distribution of the dark matter that is causing the distortion. It is a way of seeing the unseen by watching how it bends the light of everything behind it. Another method is more direct, tracing the luminous matter that clings to the dark framework. Galaxies are not scattered randomly, they are drawn to the densest concentrations of dark matter. Where we see a vast, gleaming filament of galaxies, we know it is merely tracing a much larger, much more massive filament of dark matter. The galaxies are like glitter sprinkled onto an invisible web, highlighting its structure for us to see. Modern astronomical surveys are taking this cosmic cartography to a new level. Projects like the Dark Energy Survey and the upcoming Vera Rubin Observatory are not just taking pictures of the sky, they are creating the most detailed three-dimensional maps of the universe ever attempted. They will measure the positions and shapes of billions of galaxies, allowing us to chart the cosmic web in breathtaking detail. We will see the great walls and filaments with a clarity we have never had before, and we will probe the profound emptiness of the voids. By combining the lensing technique with galaxy distribution maps, we are slowly pulling back the curtain on the universe's largest structure. This is not just about making a map, it is about understanding the fundamental rules that govern how our universe is put together. Each new survey brings us closer to seeing the full, magnificent blueprint of the cosmos. These cosmic voids are the sprawling deserts of the universe, the great empty spaces that make up most of the cosmic volume. While the filaments and nodes are the bright, crowded cities of the cosmos, the voids are the immense, silent countryside, stretching for hundreds of millions of light years. They are not perfect vacuums, but they are so sparsely populated that if our Milky Way were placed in the heart of one, our night sky would be nearly black, with only a handful of distant galaxies visible to the naked eye. One of the most famous of these empty regions is the Boötes Void, a spherical emptiness so vast it has been nicknamed the Great Nothing. If you were to place our own galaxy at the center of the Boötes Void, you would have to travel for hundreds of millions of years through near total emptiness before reaching the other side and encountering the web's bright walls. This void is so profoundly empty that it contains only a few dozen galaxies, a number that should be in the thousands. Its existence is a direct and dramatic consequence of the cosmic web's formation. As gravity pulled matter relentlessly into the filaments and nodes over billions of years, it simultaneously drained these regions, leaving behind these breathtaking bubbles of nothingness. But why should we care about these great expanses of nothing? It turns out that these cosmic deserts are not passive blank spaces. They are dynamic environments that actively shape the universe. The galaxies that reside on the borders of these voids, living on the shores of emptiness, experience a very different reality. They are isolated, cut off from the frequent interactions and gas flows that fuel star formation in the crowded clusters. This isolation means they often evolve more slowly, like quiet towns untouched by the bustle of the metropolis, becoming celestial fossils that preserve clues about earlier stages of galactic life. Furthermore, the expansion of the voids themselves holds a deep secret about the fate of the cosmos. While the entire universe is expanding, the voids are expanding faster than the denser regions around them. This accelerated growth is a key signature of dark energy, the mysterious force driving the universe's expansion to speed up. By studying the size, shape, and growth rate of these great nothings, we are essentially taking the universe's blood pressure, measuring the force that will ultimately determine its final destiny. So these voids, these great cosmic deserts, are far from being mere empty backdrops. They are active players in the cosmic ecosystem, their very emptiness sculpting the galaxies at their edges, and their relentless growth revealing the invisible force that governs everything. At the heart of the cosmic web's grand intersections lie the universe's ultimate metropolises, galaxy clusters. These are not merely collections of galaxies. They are the dense, bustling nodes where the web's filaments converge, creating the most massive structures gravity can possibly bind together. A single cluster can contain thousands of individual galaxies, all swarming in a chaotic gravitational dance. But the galaxies themselves are only the visible tip of a much larger iceberg. They are embedded within a vast, seething ocean of superheated gas, so hot it shines not in visible light, but in intense X-rays. And permeating it all is the true heavyweight, an immense, invisible halo of dark matter whose gravity is the fundamental glue holding the entire colossal structure together. We can look at famous clusters like the Coma Cluster, a sprawling city of galaxies so dense that from within it, the night sky would be ablaze with neighboring star systems. Or the closer Virgo Cluster, a vast gravitational anchor that our own local group of galaxies, including the Milky Way, is slowly falling towards. These clusters act as cosmic laboratories, places where the laws of physics are pushed to their absolute limits. The gravitational turmoil within a cluster is almost unimaginable. The immense gravity doesn't just pull on galaxies, it acts as a natural particle accelerator, whipping electrons and other particles to velocities approaching the speed of light. This creates powerful jets and lobes of radiation that we detect as brilliant radio waves and X-ray emissions, painting a picture of a truly violent and energetic environment. Yet, for all their apparent chaos, these clusters are dynamic, evolving entities. They are not static cities but growing hubs, constantly fed by a cosmic river of matter. Galaxies stream in along the great dark matter filaments, funneled towards the cluster's core over billions of years. This steady accretion is how a cluster is born and how it grows, a direct result of the cosmic web's intricate plumbing. The formation and ultimate fate of a galaxy cluster is therefore inextricably linked to the flow of matter along the web's invisible highways. By studying these brilliant, crowded nodes, we are essentially studying the endpoints of the cosmic web's grand traffic patterns, witnessing the final destination in a journey that began with a faint ripple in the dawn of time. These cosmic filaments are the great rivers of intergalactic space. They form the transportation network that fuels the universe's most vibrant cities, channeling a steady flow of raw material toward the hungry galaxy clusters. While the nodes are the destinations, the filaments are the vital highways that make the journey possible. Stretching for millions of light years, these tendrils of dark matter act as gravitational conduits, guiding both galaxies and vast reservoirs of gas along their invisible path. Much of the universe's normal matter, the stuff that makes up stars and planets and us, is not actually inside galaxies. It exists out here in the spaces between as a diffuse, superheated gas. Astronomers call this the warm-hot intergalactic medium, or the WIM. It is a thin, searing plasma, so tenuous it is incredibly difficult to detect, yet it represents a significant portion of the universe's missing ordinary matter. This hot gas is the primary cargo moving along the cosmic web. As it flows, it dictates the fate of every galaxy it encounters. A galaxy journeying along one of these cosmic rivers experiences a dramatic voyage. If it moves into a denser, more crowded environment, like the outskirts of a massive cluster, the pressure from the WIM itself can act like a powerful headwind. This can violently strip the galaxy of its own cool gas reservoir, the very fuel it needs to form new stars. The galaxy is effectively quenched, its stellar nurseries shut down, leaving it to age and redden in a process known as strangulation. Yet these filaments can also be the source of galactic life. When streams of fresh, cool gas from the WIM flow along a filament and directly pour into an isolated galaxy, they provide a new burst of fuel. This influx can trigger intense waves of star formation, lighting up the galaxy with brilliant blue nurseries. The galaxy becomes a starburst galaxy, a beacon of cosmic birth ignited by its privileged position along a cosmic supply line. This constant flow creates a stark divide in the cosmic landscape. Galaxies within the dense, gas-rich filaments are often vibrant and actively forming stars. Meanwhile, galaxies that have been cast adrift into the profound emptiness of the voids are starved of this fresh fuel, becoming quiet and passive. The filamentary network, therefore, does not just connect places, it actively shapes the lives of galaxies, determining which will thrive and which will slowly fade. Understanding these cosmic rivers is the key to understanding the entire cycle of galactic life and death, a cycle driven by the endless flow of matter along the universe's largest roads. For decades, astronomers faced a cosmic accounting error of staggering proportions. The universe's ledger was not adding up. By studying the afterglow of the Big Bang, scientists could calculate precisely how much normal matter, the protons and neutrons that make up everything we see, should exist in the cosmos today. Yet when they tallied up all the visible sources, the stars, the galaxies, and the glowing gas, nearly half of it was simply missing. It was a ghost in the cosmic machine, an entire population of atoms that had seemingly vanished. The prime suspect for this missing matter was a phantom gas hiding in plain sight, a substance known as the warm-hot intergalactic medium, or the WIM. This is not a cold, dark fog, but a searing plasma, heated to temperatures of hundreds of thousands or even millions of degrees by the immense gravitational shocks of the cosmic web's formation. It is also incredibly diffuse, with an average density of only a few dozen atoms per cubic meter, a vacuum far emptier than any we can create on Earth. This combination of extreme heat and tenuous thinness makes the WIM nearly transparent, completely invisible to conventional telescopes. So how do you find something that refuses to be seen? Astronomers turn to cosmic lighthouses, the most brilliant and distant objects in the universe, quasars. As the intense light from a quasar journeys across billions of light years towards us, it passes through these filaments of the WIM. The hot gas in these threads does not block the light entirely, but it does steal a little bit of it. Specific elements within the WIM, like highly ionized oxygen, will absorb very specific wavelengths of the quasar's light. This leaves behind a unique chemical fingerprint in the quasar's spectrum, a series of tiny, dark lines that act as a cosmic barcode. By analyzing these subtle absorption lines, astronomers can confirm the presence of the WIM, measure its temperature, and even map its distribution along our line of sight. It is a painstaking form of cosmic forensics, but it works. These observations have gradually confirmed that the WIM is real, and it is pervasive, woven through the filaments of the cosmic web. Solving the missing Baryon problem is more than just balancing the universe's books. It is a profound validation of our entire understanding of cosmic structure. It confirms that the cosmic web is not just a pretty pattern, but a functioning ecosystem, one that contains the majority of the universe's normal matter in its invisible threads. This hidden ocean of hot gas is the final piece of the ordinary matter census, the last great reservoir of the stuff that builds stars, planets, and life itself. Our understanding of this grand structure is sealed inside a digital universe. Since we cannot watch galaxies form over billions of years, we build our own cosmos inside supercomputers. These are not simple animations, they are sophisticated virtual laboratories governed by the precise laws of physics. Projects with names like Illustris TNG and Eagle start with a near-perfectly smooth universe, just moments after the Big Bang. They seed it with the same tiny density fluctuations we see in the cosmic microwave background. Then they press play. The simulation runs for billions of virtual years, calculating the gravitational pull of dark matter, the hydrodynamics of cosmic gas, and the explosive feedback from supernova and black holes. The result is nothing short of breathtaking. From that initial smoothness, an intricate cosmic web consistently emerges. Filaments of dark matter stretch across the void, galaxies spark to life along their lengths, and colossal clusters form at their intersections. It is a perfect digital replica of the real universe we observe through our telescopes. These simulations give us a God's eye view of cosmic evolution. We can fly through this virtual cosmos, watching as small proto-galaxies merge to form majestic spirals, or see how vast rivers of gas flow into the hungry nodes of galaxy clusters. We witness galactic collisions and watch as supermassive black holes flare to life at the centers of galaxies. But these digital universes are more than just confirmations of what we already know. They are powerful predictive tools. Scientists can tweak the fundamental rules within the simulation. What if dark matter behaved slightly differently? What if the influence of dark energy was stronger? By running these alternate realities, we can test our deepest theories against the one universe we see outside our window. They allow us to conduct experiments that are impossible in reality, offering a dynamic, ever-evolving model of the cosmos that helps us decipher the hidden laws that built everything we see. A galaxy's fate is sealed by its cosmic address. Its position within the vast web, from the dense urban cores of clusters to the quiet isolation of the voids, dictates everything about its life. This is environmental dependency in its most profound form. Consider a majestic spiral galaxy, similar to our own Milky Way, journeying along a filament. It is in a prime location, bathed in a steady flow of fresh gas from the cosmic rivers. This constant fuel supply allows it to form new generations of stars, its spiral arms glowing with the brilliant blue light of stellar nurseries. It is a vibrant, living galaxy. Now, imagine that same galaxy's journey takes it into the gravitational dominion of a massive cluster. As it approaches this crowded metropolis, it plunges into the superheated gas that fills the space between the cluster's galaxies. The pressure from this gas acts like a hurricane-force headwind, violently stripping the spiral of its own cool gas reservoir. Robbed of its star-forming fuel, the galaxy is quenched. Its remaining stars age together, their collective light shifting from blue to red. Over time, gravitational interactions with other galaxies in the chaotic cluster stretch and tear its beautiful spiral structure, leaving behind a featureless, rounded, red and dead elliptical galaxy. This process, environmental quenching, is the primary reason for the stark divide we see in the universe. The clusters are graveyards of galactic ambition, filled with these red and dead ellipticals. The filaments, however, are the vibrant stellar nurseries and highways where spiral galaxies can thrive. This is not a matter of chance. It is a direct consequence of the cosmic architecture. The web's gravitational currents deliver galaxies to their destinies, while its distribution of gas provides or denies the sustenance for growth. Even a galaxy's shape is sculpted by its surroundings. In the dense, violent environment of a cluster, frequent close encounters with other galaxies disrupt delicate spiral disks, morphing them into the more robust elliptical form. In the quieter filaments, a galaxy can maintain its graceful structure for billions of years. A galaxy's entire life story, from its birth to its long, slow fading, is written not in isolation, but by the invisible hand of the cosmic network it calls home. This silent, cosmic river carries our own galaxy along an invisible current. We are not sitting still in a static universe. The Milky Way, along with our entire local group of galaxies, is rushing through space at a staggering 2 million kilometers per hour. This motion is not simply the result of the universe's overall expansion. It is a peculiar velocity, a specific deviation caused by the relentless gravitational pull of the cosmic web's largest structures. We are being pulled toward a mysterious region of space known as the Great Attractor, a gravitational focal point hidden behind the dust and stars of our own galactic plane in the constellation Centaurus. This unseen concentration of mass exerts a force so immense it dictates the motion of thousands of galaxies, including our own. But what exactly is pulling us? The Great Attractor is not a single, monstrous object. It is the collective gravitational weight of a vast supercluster of galaxies, a dense knot in the cosmic web known as the Laniakea supercluster. This is our true cosmic address, a sprawling metropolitan area of the universe containing over 100,000 galaxies, all flowing towards its massive center. Our journey toward this gravitational anchor is the most direct proof we have that the web's architecture is not a fossil. It is a living, dynamic structure whose gravitational tides continue to orchestrate motion on the grandest scales. By meticulously measuring the peculiar velocities of countless galaxies, astronomers can perform a form of cosmic cartography. They trace the paths of these galactic streams backward, mapping the flows to reveal the hidden topography of dark matter that guides them. These grand rivers of galaxies are like leaves floating on a vast, invisible river, their drift betraying the powerful, unseen currents beneath the surface. Watching this slow-motion galactic ballet is like feeling the universe's pulse, a steady rhythm of gravity that has been beating for billions of years and continues to shape our path through the cosmos. This grand cosmic architecture will not last forever. The same force that reveals the voids is also weaving the web's ultimate demise. Dark energy, the mysterious pressure causing the universe's expansion to accelerate, has seized control of the cosmos's future. For billions of years, gravity was the undisputed master builder, pulling matter together to construct the web. Now, a cosmic tug-of-war is underway, and dark energy is winning. The expansion of space itself is stretching the very fabric of the cosmic web. Over tens of billions of years, this accelerating expansion will pull the universe apart. The great dark matter filaments, those cosmic highways that have channeled matter for eons, will begin to stretch and thin. They will become like a piece of elastic pulled from both ends, growing more tenuous with every passing moment. As the filaments are stretched, the flow of gas along them will slow to a trickle and then cease entirely. The cosmic rivers that once fed galaxy clusters will run dry. Galaxies on the outskirts of these great metropolises will find their supply lines cut, their journeys along the web halted by the increasing vastness of the voids. The clusters themselves, those brilliant nodes, will not be torn apart as their gravity is strong enough to hold them together, but they will become isolated islands, drifting further and further apart in an ever-darkening sea of nothingness. The cosmic web, this magnificent network that connects the universe, will slowly fray and dissolve. We can project this forward to the universe's possible final states. In one scenario, the heat death, the expansion continues until the universe becomes a cold, dark, and nearly uniform soup of diluted particles. Every star has burned out, every black hole has evaporated, and the cosmic web is a faded memory, its structure erased by relentless expansion. In a more extreme fate known as the Big Rip, dark energy grows so powerful that it overwhelms all forces, not just gravity. It would first tear galaxy clusters apart, then galaxies, then solar systems, and finally, it would rip apart atoms themselves, shredding the very fabric of spacetime. While this is a more speculative end, both scenarios point to the same conclusion. The era of structure building is finite. We are living in a cosmic golden age, a brief window in the universe's history where the lights are on and everything is connected. The vast cosmic web, for all its grandeur, is a temporary phenomenon. It emerged from the faintest of whispers in the early universe, flourished for countless eons, and will one day fade back into the silence from which it came. Yet the cosmic web's existence presents a profound challenge to the very laws of physics we hold dear. Could our entire understanding of gravity be wrong? This is not a fringe question, but a serious scientific pursuit championed by physicists like Mordechai Milgram. He proposed an alternative called modified Newtonian dynamics, or MOND. This theory suggests that we do not need any mysterious dark matter to explain the motions of galaxies. Instead, gravity itself behaves differently at extremely low accelerations, like those found in the outskirts of galaxies. In this view, the force of gravity does not fade as quickly as Newton and Einstein predicted. This single change can explain why stars in the outer regions of spiral galaxies orbit so quickly, matching Vera Rubin's observations without invoking an invisible halo. For individual galaxies, MOND is surprisingly effective, but can it build a universe? The true test for any cosmological theory is whether it can generate the intricate, large-scale structure of the cosmic web. This is where MOND and its relativistic extensions face their greatest hurdle. The prevailing dark matter model, with its invisible scaffolding, naturally and consistently produces the filaments, nodes, and voids we observe in supercomputer simulations. The gravitational pull of dark matter is the essential ingredient that gathers ordinary matter into those vast, interconnected structures. Reproducing this specific architecture without dark matter has proven incredibly difficult. While some modified gravity simulations show promising hints of filament-like structures, they often struggle to match the precise richness and scale of the cosmic web we see. The brilliant, dense galaxy clusters and the profound emptiness of the voids present a monumental challenge. Proponents of modified gravity continue to refine their models, searching for a way to forge the universe's largest structures with a rewritten law of gravity. This intellectual struggle is not a weakness of science, but its greatest strength. These alternative theories force us to question our most fundamental assumptions. They push the dark matter paradigm to provide even more precise and testable predictions. Is the cosmic web we see truly impossible to build without an invisible builder? Or is it evidence of a deeper, more complex law of gravity waiting to be discovered? The cosmic web is more than a structure. It is the ultimate arbiter in a grand debate about the nature of reality itself. This intricate cosmic architecture might be far more unique than we ever realized. The specific pattern of our universe, the precise scale of its filaments, and the staggering emptiness of its voids could be a direct consequence of a set of fundamental numbers. These are the physical constants, the immutable rules of reality like the strength of gravity and the force binding atoms. Tweak just one of these numbers and the entire cosmic web unravels. This leads to a staggering possibility that our universe with its specific web is just one page in an infinite book of realities, a concept known as the multiverse. In other cosmic realms born with different constants, the tapestry of existence would be woven with entirely different threads. A slightly stronger gravitational constant might have caused the universe to collapse back on itself in a fiery crunch long before any web could form. A slightly weaker one, and the initial ripples might never have gathered enough pull to form even the first galaxy. In those alternate realities, space could be a formless, expanding fog of isolated stars or a single, monstrous black hole. There would be no great walls, no glittering filaments, no vast voids. Our cosmic web, in all its splendor, is not an inevitable structure, it is a signature. It is the direct output of our universe's particular settings, a fingerprint proving that our physical laws are tuned in a very specific way. This tuning connects the largest scales to our own existence through the Anthropic Principle. It's the philosophical idea that the universe we observe must be compatible with the existence of observers like us. A universe without a cosmic web would lack the complex structures necessary to forge planets and foster life. We could not exist in a cosmos that failed to build the very filaments that birth and feed galaxies. So when we gaze upon this immense network, we are not just looking at a structure in our universe. We are looking at a prerequisite for our being. The cosmic web becomes the ultimate evidence that our universe is a special place, not necessarily at the center of creation, but finely tuned to allow for the emergence of complexity and ultimately life itself. Making this invisible architecture visible requires a special kind of magic. Science visualization artists are the modern-day cartographers of the cosmos, translating trillions of data points from galaxy surveys into breathtaking journeys we can all experience. At planetariums around the world, audiences don't just hear about the cosmic web, they fly through it. The dome becomes a window, and you are launched from the familiar stars of our night sky, rushing past swirling galaxies and out into the deep void. Soon, a faint, glowing lattice emerges in the darkness, a three-dimensional tapestry of delicate threads and brilliant nodes stretching to infinity. You can see how galaxies cling to the filaments like pearls on a string, and how those threads converge into the blazing metropolises of galaxy clusters. This is not an artist's guess, it is a data-driven reconstruction, a visual translation of the universe's true structure. Institutions like the American Museum of Natural History have perfected these immersive simulations, turning abstract cosmological models into a sensory experience that feels almost physical. The goal is not just to inform, but to evoke a sense of awe, to make you feel the sheer scale and interconnectedness of the cosmos in your bones. For a student sitting in that planetarium seat, this can be a life-changing moment. That visceral understanding of the cosmic web can ignite a passion for astronomy, physics, or computer science, inspiring the next generation to ask the big questions. By transforming complex data into a shared visual story, we ensure this grand discovery belongs not just to scientists, but to everyone. The invisible framework of our universe becomes a source of collective wonder, a reminder that we are all part of something vast, beautiful, and brilliantly structured. Our own existence might be a direct product of this cosmic architecture. Every atom of oxygen in your lungs, every particle of carbon in your cells, was forged in the heart of a long-dead star. But how did these essential ingredients for life escape their stellar forges and travel across the universe to end up here? The cosmic web provided the delivery system. When massive stars explode as supernova within galaxies, they blast these newly created heavy elements out into the vast intergalactic medium. This enriched gas then flows along the web's filaments, carried by those same cosmic rivers that feed galaxy formation. A planet forming around a new star in a quiet spiral galaxy is, in effect, receiving shipments of life's building blocks that have traveled millions of light years along these invisible highways. This cycle of stellar death and galactic recycling means the cosmic web is not just a structure of matter, but a circulatory system for the very elements of life. Without this large-scale distribution network, the raw materials needed for planets and biology might remain locked away in isolated pockets of the universe, never meeting and mixing to create the complex chemistry we represent. This leads to a profound question about location. Is every place in the web equally suitable for life? Astronomers theorize about galactic habitable zones, regions within the cosmic architecture that are just right for fostering biological evolution. A galaxy's position within the web is everything. Imagine a galaxy sitting in the dense, violent core of a massive cluster. It is constantly bombarded by radiation from its numerous neighbors, and its planetary systems are frequently disrupted by close gravitational encounters. The environment is simply too chaotic and hostile for life to gain a stable foothold over billions of years. Now, consider a galaxy residing in a quieter suburb, along a filament but far from the crowded urban centers. Here it can enjoy a steady but not overwhelming flow of enriched gas. It is isolated enough to avoid constant galactic harassment, yet still connected enough to receive the necessary chemical ingredients. This peaceful, stable environment provides the extended periods of cosmic calm that life likely requires to emerge and evolve. Our own Milky Way seems to occupy just such a Goldilocks zone within the Laniakea supercluster, not too close to the frantic core and not lost in the utter isolation of a void. This perspective ties the fate of a single planet directly to the largest structure in the universe. The cosmic web does more than connect galaxies. It may very well define the safe galactic neighborhoods where the miracle of life is given a chance to begin. For all its grandeur, the cosmic web is a map filled with blank spaces. We have traced its outlines, but its deepest nature remains shrouded in secrets. The identity of dark matter, the master architect, is the most profound mystery. We know it holds the universe together, but we do not know what it is. Is it a sea of exotic, undiscovered particles, trillions of times lighter than an electron, constantly streaming through our bodies without a trace? Or is it something even stranger, a fundamental flaw in our understanding of gravity itself? Decades of sensitive experiments deep underground and powerful particle collisions in accelerators have so far failed to capture a single dark matter particle. Its elusiveness is a constant, humbling reminder of how much we have yet to learn. Then there is the puzzle of the baryons, the ordinary matter that makes up our world. We know this gas flows along the dark matter filaments, but the exact physics of how it cools, condenses, and ultimately collapses to form galaxies is a messy and complex process. Supernova explosions and ravenous black holes at the centers of galaxies inject tremendous energy back into their surroundings, violently disrupting the very gas that feeds them. This feedback can halt star formation entirely or, paradoxically, trigger new waves of it. Getting this intricate dance right in our simulations is crucial, and we are still learning the steps. This leads to another nagging discrepancy between our models and the real sky. Our most sophisticated simulations predict that thousands of small, dwarf satellite galaxies should be orbiting large galaxies like our Milky Way. Yet when we look, we only find a few dozen. Where are all the missing satellites? This could mean our understanding of how small galaxies form is incomplete, or perhaps that some process destroys these fragile dwarfs early in the universe's history. Looming over all these questions is the enigma of dark energy, this mysterious force which makes up the majority of the universe's content, is causing the cosmic expansion to accelerate. But what is it? Is it a constant property of empty space itself, as Einstein once proposed and then discarded? Or is it a dynamic energy field that has changed over cosmic time? Its behavior will ultimately decide the final fate of the entire cosmic web, yet its fundamental nature is one of the biggest unsolved problems in all of physics. Each breakthrough in mapping the web does not bring final answers. Instead, it peels back a layer to reveal new, deeper puzzles waiting beneath. Our exploration of this vast cosmic architecture is far from complete. It is a living, breathing detective story written on the scale of the universe itself, and we are only just beginning to read the pages. This cosmic architecture, for all its scientific weight, is also a thing of astonishing beauty. The branching filaments and glowing nodes do not look like a random accident. They look like a design, a universal art form sculpted by gravity itself. Look closely at a map of the cosmic web, then look at a photograph of the interconnected neurons in a human brain, or the sprawling branches of a river delta from the air. The resemblance is uncanny. It is as if the same fundamental pattern has been stamped onto reality at vastly different scales, from the microscopic to the cosmic. This self-similarity, this fractal-like repetition of form, is not a mere coincidence. It hints at a deeper truth about our universe. The same simple, elegant physical laws that govern the flow of electricity in a nerve cell also govern the flow of matter along a dark matter filament. The principle of finding the most efficient path, of minimizing energy, of forming networks, appears to be a universal rule. This has not gone unnoticed by the world of art. Digital artists and data visualizers have taken the raw numbers from galaxy surveys and transformed them into immersive, breathtaking experiences. They render the cosmic web in swirling nebulae of color, turning cold data into a warm, tangible vision. These works are more than just pretty pictures. They are a bridge connecting the analytical mind to the emotional heart, allowing us to feel the grandeur of the structure in a way raw data never could. Philosophers and thinkers see in this pattern a reflection of a deeply ordered cosmos. It suggests that complexity and beauty are not rare exceptions, but fundamental outcomes of the universe's operating system. The cosmic web is a masterpiece written in the twin languages of gravity and dark matter. To appreciate its aesthetic splendor is not to abandon science, but to deepen our connection to the cosmos. It merges our relentless inquiry with a pure, humbling sense of wonder, reminding us that we are not just studying the universe, but are an intimate part of its magnificent, patterned whole. This intergalactic medium is the original stuff of the universe, a primordial haze of hydrogen and helium that fills the cosmic web. After the Big Bang, this gas was dark and neutral, a cosmic fog that shrouded the early cosmos. Then, a few 100 million years later, the first stars and galaxies ignited. Their intense ultraviolet radiation began to flood the universe, a brilliant dawn that ripped electrons away from the atoms in this vast fog. This was the Epoch of Reionization, a universal transformation that heated and illuminated the gas, turning the dark, neutral hydrogen into a transparent, glowing plasma. This process cleared the cosmic fog, making the universe transparent to light and completing the last major phase transition of the cosmos. We can still observe the aftermath of this ancient upheaval by looking at the most distant quasars. As a quasar's powerful beam of light travels for billions of years to reach us, it passes through countless filaments of this intergalactic gas. The neutral hydrogen that still remains within these filaments acts like a cosmic filter, absorbing very specific wavelengths of the quasar's light. The result is a stunning pattern etched into the quasar's spectrum. Instead of a smooth rainbow of color, we see a dense, dark forest of absorption lines, each one a fingerprint from a single cloud or filament of hydrogen the light has passed through. Astronomers call this the Lyman alpha forest. This forest is not a random thicket. It is a precise barcode that encodes the density, temperature, and velocity of the gas along that specific line of sight. By studying many quasars from different angles, we can piece together a three-dimensional tomographic map of the cosmic web's gaseous skeleton. This tenuous plasma is far more than a remnant. It is the active bloodstream of the cosmos. This gas is the raw fuel for future generations of stars. It circulates the pristine hydrogen and helium, along with heavier elements blasted out by supernova along the web's invisible highways. When a galaxy lies in the path of this flowing intergalactic medium, it can accrete this fresh fuel, sparking new rounds of star formation and ensuring the cosmic cycle of birth and renewal continues. The web is not a static sculpture, but a living, breathing entity, and this invisible gas is the breath that gives it life. Deep within the heart of nearly every galaxy, a silent titan waits. A supermassive black hole containing the mass of millions or even billions of suns compressed into a single point. When this monster feeds, it does not do so quietly. As vast clouds of gas and stars are pulled into its gravitational grip, they don't just vanish. The material swirls into a superheated, glowing disk of doom, frictional forces heating it to millions of degrees before it crosses the event horizon. In this active state, the black hole awakens, transforming into a quasar or an active galactic nucleus, becoming one of the most luminous objects in the universe. But its influence extends far beyond its host galaxy. The energy unleashed by this cosmic engine does not just radiate as light. It can trigger colossal outflows, launching jets and winds of charged particles that scream out into intergalactic space at nearly the speed of light. These outflows travel for thousands, even millions of light years, slamming directly into the delicate filaments of the cosmic web. The impact is like a supernova on a galactic scale. This immense influx of energy heats the thin gas within the filaments, preventing it from cooling down. And if the gas cannot cool, it cannot condense under gravity to form new stars or fuel existing galaxies. This process is known as AGN feedback, and it acts as a cosmic thermostat. It is a self-regulating mechanism that prevents galaxies, especially those in massive clusters, from growing too large too fast. Without this powerful shutdown switch, the most massive galaxies would devour all available gas, becoming bloated giants that would utterly dominate the cosmic landscape. But the role of these black holes is not purely destructive. Those same powerful outflows do something else remarkable. They act as cosmic delivery trucks, carrying heavy elements forged in stellar interiors and supernova explosions. They blast this enriched material, the very stuff of planets and life, out of the galactic core and far into the intergalactic medium, seeding the cosmic web with the seeds of future complexity. A supermassive black hole is a paradox, a force of immense destruction that also sows the seeds for new creation. Its relatively tiny domain exerting an influence that cascades across the largest structures in existence, proving that even the smallest components can shape the grandest designs. Every distant thread of this cosmic web is a message from the past. The light from a galaxy millions of light years away shows us not what it looks like today, but what it looked like millions of years ago. By pointing our most powerful telescopes at the deepest, darkest patches of sky, we are essentially building a time machine. The Hubble Space Telescope's iconic deep field images were our first real look back at the universe's childhood, revealing a cosmos filled with small, irregular, and violently colliding infant galaxies. Now the James Webb Space Telescope peers even further back to an era when the cosmic web was still under construction. In these incredible images, we do not see the clean, defined filaments of the modern web. Instead, we see a chaotic construction site. Faint, wispy tendrils of gas are beginning to condense along the invisible dark matter scaffolding. We see proto-galaxies, not yet fully formed, strung along these threads like beads on a wet string, slowly sliding toward the gravitational anchors that will become the great clusters of the future. This temporal view is the ultimate test for our cosmic models. Does the infant web we observe match what our simulations predict? The answer is a resounding yes. We see the hierarchy of structure formation unfolding exactly as forecasted. Tiny clumps of matter merge into larger ones. The delicate filaments thicken and strengthen over billions of years. The voids already present begin to empty out even more. Watching this cosmic growth confirms that the entire magnificent structure did indeed grow from the tiniest of seeds, the quantum ripples imprinted at the dawn of time. The cosmic web is therefore more than a map of space. It is a living history book. each layer we observe at a different distance adds another chapter to the story, chronicling the universe's journey from a smooth, hot soup to a complex, structured network of galaxies, all recorded in the timeless language of light. Our own cosmic address is far from the bustling center of the universe. The Milky Way resides in a quiet galactic suburb, a peaceful neighborhood on the outskirts of the immense Laniakea supercluster. This supercluster is our true home, a sprawling continent of space containing over 100,000 galaxies, all bound together by gravity's invisible threads. We are not in a dense urban core, nor are we lost in the profound isolation of a void. Instead, our local group of galaxies, including Andromeda, floats within a minor filament of this grand structure, a side street in the cosmic metropolis. This specific location has profoundly shaped our galaxy's history. While the cores of massive galaxy clusters are chaotic environments, full of violent collisions and intense radiation, our quiet corner has offered a stable environment for billions of years. This cosmic peace has likely been a crucial ingredient for life on Earth, allowing our solar system to form and evolve without being constantly disrupted by close encounters with other galaxies. Yet, even from our quiet street, we are not motionless. Our entire local group is on a slow, relentless journey, pulled by gravity toward a mysterious region known as the Great Attractor. This is not a single object, but a massive gravitational weight, a dense knot in the cosmic web hidden behind the dust of our own galaxy. We are flowing along an invisible current, part of a vast river of galaxies, all moving toward the same focal point. This journey is the most personal evidence we have that the cosmic web is a dynamic, living structure. To know our place in this architecture is to gain a humbling new perspective. We are not at the center of anything, but we are profoundly connected to everything. Every galaxy we see in the night sky is part of the same vast network, a single thread in a tapestry of unimaginable scale. Our existence on a tiny planet orbiting an average star in a quiet galaxy is a direct product of our specific location within this cosmic whole. Our journey through the cosmic web reveals a universe of breathtaking connection. From the faintest whisper of a quantum fluctuation to the invisible scaffold of dark matter, we have traced the architecture that binds every galaxy into a single dynamic whole. This is not merely a map of where things are, it is the story of how everything came to be. The cosmic web is the fundamental framework of reality, the engine of galaxy birth, and the river system that delivers the very elements of life. We are, in the most literal sense, children of this network. The iron in your blood, the calcium in your bones, every atom that constitutes our world was forged in ancient stars and then distributed across the cosmos along these vast, invisible filaments. Carl Sagan's poetic truth that we are made of star stuff finds its ultimate expression here. We are not just living in the universe is living within us, a legacy of the cosmic web's grand design. So the next time you gaze into the night sky, remember you are not looking out at a void. You are looking at our home, a single thread in a magnificent, glowing tapestry. Let us know what part of this cosmic story resonated most with you in the comments, and subscribe to continue exploring the deepest mysteries of